As you know, Amanda Hughes is our speaker for today, and it's my great pleasure to have the opportunity to introduce her to all of you. She joined the department in 2016 as a research scientist, and then in 2019 became assistant professor of practice. And this is such a natural because in her role, she draws upon, among other things, many other things, her experience with Chevron exploration in the New Ventures Group. She was with Chevron for 3 years, from 2013 to 2016, following her PhD work. And in that environment, applied her specialty area of structural geology, including all kinds of modeling, which you'll see and hear about, with seismic reflection interpretation. So it was an amazing kind of a postdoctoral experience extended that allowed her to basically take her expertise in structural geology and expand it even more into geophysics. Amanda carried out her undergraduate work at Washington Lee University. I had the pleasure of lecturing there a number of years ago, and it's just a beautiful place. And furthermore, they've got a lot of money. They have alum that really feed a lot of money into that department, a department of undergraduate students who are working with state-of-the-art equipment, travel budgets, and so on. She worked there with Chris Connors. Chris Connors was her senior thesis advisor. And then she went on to Harvard, where she worked with John Shaw. And at Harvard, where she received her PhD degree, she addressed fold mechanics and kinematics in relationship to structures that were imaged and interpretable in terms of seismic reflection data. After Chevron, we were lucky enough to be able to recruit her here. And what she brings to the department is a broad range of structural geological subdisciplines and methodology, and a DNA of really enjoying and wanting to work, as you'll see today, with a broad range of geoscientists. As most modern structural geologists, she works in a span of scales, temporal and spatial. She's a hardcore structural geologist and continues to work at the cutting edge in terms of kinematic and mechanical analysis. And she retains that first order interest as well in geophysics, not only with respect to seismic reflection, but also active tectonics and earthquake geology, earthquake seismology. I have personally enjoyed any number of collaborations with Amanda. They include an ongoing project with 18 folks all together working on the complexities of the Rincon Mountains. But in addition, Amanda and any number of us have enjoyed working within the sphere of Pete Reiner's Keck project in the Paradox Basin, with the modest task of trying to work out structural, tectonic, and fluid flow history over the last 300 million years. And this has required not only pulling together so many different disciplines broad across the earth sciences and departments like hydrology and geosciences, but also working on so many different aspects with graduate students, with adjunct faculty. I'm thinking of Bob Kranz and Steve Lindgren to try to pull things together. Those of us who love structural geology enjoy in the Moab region getting together and being nerds, structural geology nerds, and really going into some of the structural details. Amanda's talk today is entitled Distinctive Structural Phenomena in Evaporite Systems, Examples from the Paradox Basin.
Well, thank you so much, George. That was such a nice introduction, far nicer than I could have imagined. But as George said, I've been really lucky to work on this project with this big group of collaborators. And the broader project has been focused on paleofluid migration and how that relates to the evolution of the basin. And I couldn't possibly do the whole scope of the project justice, and I wouldn't want to ruin the surprise for any of our geochemists and economic geology collaborators. So I hope that they'll be giving talks here in the future too, but I'm going to focus on the structural components of it. And in particular, I'm going to focus on the evaporites in the basin and how, if you've never had the pleasure of working in an evaporite basin, how they are weird and wonderful and lead to some really distinctive structures and some really profoundly interesting opportunities to solve some tricky problems in structural geology. So anything you like in here was one of my collaborators, and anything that I misrepresented, that's on me. So. And I want to especially point out, especially towards the end, my PhD student, Lauren Rear, has done a whole bunch of the data collection on the last part of this that I'm going to talk about. And you'll see her outstanding work here towards the end. So why work in the Paradox Basin, aside from the fact that it is one of the most lovely and beautiful places that you could possibly work? The site of Arches National Park, of course, with the iconic arch, Canyonlands National Park, Natural Bridges National Monument, and just plain old off a dirt road in the Bureau of Land Management, it's still spectacularly beautiful. And so that's part of the motivation to want to work there. But there's other very good reasons to work in the Paradox Basin. First of all, it has outstanding rock to tree ratios, rock to plant ratios, and rock to people ratios. So I'm a big fan of it from all of those perspectives. And then additionally, it is a salt basin that has been exhumed several kilometers, and so is a really outstanding analog to a lot of the subsurface challenges in lots of applied systems in stratigraphic, in sedimentary basins all over the world. And so it's been used as a place for analog studies for a long time. And as you can see, the exposure of the geology is outstanding. There's spectacular outcrop exposure and continuity that you can be really confident of what you're looking at in terms of folds and faults. Of course, this is the iconic, in every textbook, outcrop of the Moab Fault. And there are beautiful outcrops of faults themselves. Here's Steve giving us a nice strike, dip, and rake on the Moab Fault right outside of Arches National Park, and beautiful second order damage structures associated with these faults. And additionally, there's lots of beautiful outcrops of fractures, which I'm going to talk about a lot today. And in addition, it's not just all structure, although some of us, I'm sure, wish it was. Just kidding. There are fantastic outcrop expressions of the role that different kinds of fluids have played on modifying the rock system over time. And so we can see here some reducing fluids, which have reduced red beds to now be bleached. And you can even see hydrocarbons in here in this dark gray ledge, which was the picture I showed in the BLM before. You can see more evidence of these bleaching fluids and the fact that they use structures to migrate, because those provide permeability pathways. And there are lots of other kinds of fluids in the basin too. There are ore-forming minerals like uranium and vanadium that have been transported by fluids of different kinds of geochemistry. There are hydrocarbons, and different kinds of fluids and timings of fluids, yet again, have mobilized and reprecipitated other economically important elements such as copper and iron and manganese. And so all of these different manifestations of fluid flow are related to the temporal evolution of the basin over time, and how different kinds of fluids were generated from different kinds of geologic phenomena, and then therefore got expelled and ended up in different parts of the rock record to concentrate these economically important minerals. So here's this beautiful summary map that's from Isabel Barton, just showing the extents of the Paradox Basin. The outline in the dashed here is the extent of salt in the basin. And then over here are plotted all these different occurrences of uranium and vanadium in yellow, copper in red, manganese and iron in gray, as well as the outlines of oil and gas fields, CO2 fields. There's also lithium deposits here as well. So it's just full of all kinds of good stuff. So let's get a little bit into the geologic history of the Paradox Basin. It's a foreland basin to an ancestral Rocky Mountains uplift called the Uncompahgre Uplift, which lies to its northeast up here. What you can see here is a cross section at the location of the red line here, where you can see that the distinctive structures in the basin are salt features. And so what's outlined in this dark pink are these salt wall structures, where salt is in the current day either at or very close to the surface. And they form these very vertically continuous features that are very distinctive of salt structures. So as I mentioned, it's a foreland basin to the Uncompahgre uplift. If we look at a paleogeographic reconstruction here from Ron Blakey, you can see the Uncompahgre uplift here, and the Paradox Basin formed this restricted marine setting, which temporarily closed off and then reflooded in a series of cycles of about 30 cycles that formed the sequential deposition of halites and black shales that form the Paradox Formation. And then immediately after that, the basin, due to erosion and removal of material from the Uncompahgre uplift and the adjacent ancestral Rocky Mountain uplifts, the basin filled in and became a terrestrial setting. Now, the interesting thing about this was the massive amount of salt that was deposited in this basin and what makes this so special. So this is the crux of the talk. Salt is weird and wonderful, and it behaves unlike almost any other rock type. And in particular, it's anomalously weak. And so if we look at a typical strength depth plot in structural geology, we know that strength usually monotonically increases with depth until we reach the brittle ductile transition. Now, if we zoomed way in on the axis of this, what we would see is that as most rock types increase monotonically with depth in the brittle portion, even these shales here are still getting strong. Salt has undergone its brittle ductile transition at about 100 meters depth, which means if you put almost any load on top of salt at all, it's going to immediately ductily deform. It can't sustain any shear stress. And so it provides a really unusual situation for basins that host it in terms of how they evolve. Additionally, it has nearly constant density with depth. Its thermal conductivity is high. So it's a very strange thing that leads to strange geologic phenomenon. So if we just look at this cartoon of how these salt structures evolved, the salt is going to be shown here in pink, and we're looking at the Uncompahgre uplift over here, the basement involved ancestral Rocky Mountain uplift in gray. And as you started to erode off of that and shed sediments off into on top of the salt, immediately the gravitational load associated with that sedimentation caused it to sink, and that caused ductile deformation of the salt, which displaced the salt, creating a salt high outboard of that, which then further caused depression here. So you have a positive feedback system where you're continuing to trap sediments here proximal to the uplift and creating a salt wall. Now that process continues to take place until eventually you'll breach over the salt wall at some point and you'll start loading there. And you will form this series of progressive salt walls in here that will ultimately have a geometry something like this, very vertically exaggerated, of course. But the interesting thing to mention about this is the fact that these are growing by passive diaperism. And so in this case, you know, it used to be the idea that salt diapirs were punching their way up through sediments, but we know from the strength of salt that that's impossible because salt is so much weaker than the sediments around them. So instead, what's actually happening is that diapir is sitting in one place and the sediments are subsiding down around it. And so the height of these salt walls reflects something of the original thickness of the salt that was deposited in the first place. And so this is a process called passive diaperism. And this is really unique to salt basins as a function of their distinctive mechanical strength. Additionally, if we look at, we can see the record of that syntectonic sedimentation, and they form what are called halokinetic sequences. So these sediments are progressively subsiding and rotating as these mini basins are subsiding, and we can see evidence of that. Here's a really nice mapping done by Jesse Thompson-Job and others that just came out in 2020 of the Sinbad diapir, which is this structure right here. And if we zoom into the edge of this, what we can see is this is a line tracing based off of seismic reflection data. We can see this progressive rotation of the sediments that were deposited while these mini basins were subsiding down into the salt. If we zoom in right here and see what that looks like in outcrop, what we can see is that in the Permian, Pennsylvanian Cutler Formation, you can see that the dips progressively get shallower, and there's a series of onlap unconformities in here that are documenting that progressive subsidence and rotation of the mini basin over time during salt wall passive diaperism. So this process will continue to occur until the mini basin reaches the basement, at which case it runs out of salt. And so it can't feed this salt wall growth anymore, and it stops and it forms a weld. That will happen here too. And once that has happened and it's welded on both sides, there's nothing to feed the further growth of that salt diapier. And so sediments can deposit straight across the top of this. And that continues to be the case until you can deposit sediment straight across the basin. And unless something else happens to the basin at this point, it will just continue to load sediments across the top. And indeed, that is what's happened in the Paradox Basin through the parts of the Jurassic. The sediments are relatively constant thickness across the entire basin that tell us that most of these salt walls have welded by that time. And so, that was just a cartoon of what's going on, but we've reconstructed a three-dimensional model of the basin using a series of published and original crossings, wells, which are shown here in red. This is just a little snippet out of the 3D model showing Salt Valley, which is where Delicate Arch sits right around here. And this kind of gives you an idea of what the basin model looks like. So we have wells that tell us what formations we're encountering at what depths, and we use that to construct these balanced cross sections, which we can then merge into a three-dimensional model. And so if we take a look at that three-dimensional model, this is a perspective view of it, looking at the top of the Paradox Formation, which is the salt, colored by elevation. So red is high and blue is low. And what we can see in the basin here is that we can see the salt walls really clearly. That's where the salt is high, where it's red. Adjacent to them on either side are blue welds that we can see right there that form when the mini basins touch down on the underlying Mississippian section. And then there's these Lasalle volcanics I wanted to mention in case you wondered what that unusual shape is in the middle, and those come a lot later in the basin. So what you can see is that when you look at this basin, unlike a typical sedimentary basin where the thicknesses of sediments are relatively constant, we see rapid variations in the thickness of the salt because it deformed while the other sediments in the basin were being deposited. And so in some places, like in Salt Valley, the salt is up to 4 kilometers, whereas 10 kilometers away, the salt has no thickness at all. And so this has some really interesting implications that we're going to look at here in a little bit. So as I mentioned before, because you've welded in between the salt walls, then nothing will happen and the basin will just fill up with sediments unless there's a tectonic push or erosion comes down and reaches the level of the salt again. And of course, we know adjacent to the Paradox Basin that there was such a tectonic push. We know that the laramide orogeny was responsible for creating basement-involved uplifts much more recently. And so this is just an example of one of those uplifts. This is Combe Ridge, the monument uplift, which lies just to the south of the Paradox Basin and extends underneath the salt into the basin itself. And so we know that the laramide orogeny involved basement. We know from looking at the relative structural elevation of some of these sediments that maintain their thickness, that they have been uplifted during the laramide above, for example, the Uncompahgre uplift was reactivated in the laramide. But there was always this question as to what was happening in the basin during the laramide. And the reason for that is that salt can hide shortening. It's called cryptic shortening because the salt is so weak, it can shorten without forming the thrust faults that you might expect more traditionally in shortening systems. Now, one of the hints that we have for reactivation inside the basin and the laramide is underneath Lisbon Valley. There's a 3D seismic reflection survey that was published in a master's thesis. in 2015 that shows offset of the basement sitting underneath Lisbon Valley in a thrust sense. And so reactivation of some of those previously normal faults as thrust faults. So that's some evidence for it. But then the other question is, what happened to the rest of the basin? So when that shortening occurred, we know they're shortening here. We can see it in the seismic here, and we can see it here as well, based on the shortening and folding of the overlying sedimentary sections. And we can visualize that with these trippy looking maps that I included here. So what this is the top of the Cretaceous Dakota Formation we've reconstructed based off of our cross sections over the whole 3D basin. And it's a structure contour map, but what I've done is colored it by dip magnitude. And so you can see some places where the dip of the Dakota is flat. That's black right here. And we know that because the Dakota relatively maintained a regional thickness across here, that it was deposited when things were relatively flat. But what we can see when we look at the Dakota now is significant amounts of folding that has occurred adjacent to the salt structures. So the salt structures you can see because the faults are on here, and the faults kind of outline the current trend of the salt walls. So you can see adjacent to the salt walls, there's been a significant amount of folding that must have been associated with the laramide, at least post deposition of the Dakota. And so here we can also see that the places where the dip changes, this is the azimuth of the dip direction, is associated with anticlines over the salt walls and synclines in the mini basins in between. So this is an amplification of the salt walls. Additionally, we form some other pretty unique structures when we shorten salt walls. One of those are these transverse structures. So when we shorten salt, you can imagine that if there's differences in shortening along strike, you'll form tear structures, which are typical of sedimentary basins. But additionally, in salt basins, analog modeling has demonstrated that you'll also form these transverse structures right at the crest of shortening salt structures that will be parallel to the shortening direction. And we see examples of those like in the map from Jesse Thompson-Job in Sinbad Valley. So after the laramide, there was burial by the Maine Coast Shale, a big thick shale associated with the Cretaceous Interior Seaway. There was later a period of extension, which was associated with the formation and primary amount of slip on some of the big fault structures in the basin, like the Lisbon Valley and the Moab Fault. And then there was late rapid exhumation and erosion within probably the last 10 to 6 million years to present, and which is ongoing. That erosion has cut down to the level of the salt, exposing the salt, which is soluble. And so the salt is dissolving and you get dissolution related collapse and formation of normal faults along the flanks of the salt walls to accommodate that. That process is ongoing. If we look here, this is an INSAR image of the Canyonlands, where we can see the faults here are associated with a significant rate of motion as the river has cut down to the level of the salt and is actively dissolving the salt away associated. And so therefore you have collapse of the overburden down towards the river. So all of this process has led to the migration of fluids in the basin, and the timing and nature of those fluids has to do with the particular types of things that are being buried and the types of fluids that are therefore being expelled over time. There are many different sources for that. There are the source rocks, which are interbedded with the salt. There are waters being driven off by clay dewatering, and there are also the structures that have focusing effects and also provide permeability pathways for these fluids. And we can see that the structures are critically important to the migration of these fluids because we can see bleaching fluids and iron manganese oxides and copper all intimately associated with the structures. And so if we want to understand how these fluids take advantage of these structures, first off, we have to understand how these structures formed, and how they formed as a function of the state of stress in the basin over time. And so we can look at the current day state of stress in the basin. If we look at this study by Zoback, we can see the maximum horizontal stress direction is about west-northwest, east-southeast in the Paradox Basin. And if we think to, how we could look at the state of stress in other paleostress cases, we might look at regional fracture sets, right? And if we think back to some of the classic studies of regional fracture sets, we know that they can be laterally continuous and representing a regional stress orientation over really large areas, maybe hundreds of kilometers, as in this example from the Appalachian Foreland and Fulton Thrust Belt. However, salt is very weak and therefore has a really strong effect on the orientation and state of stress in the basin. So here's just a little snippet of a boundary element model that I ran. The top of salt is in purple, and you can see that the salt is plunging off here towards the side, and there's a little fault here. And what's shown here in these little sticks are the orientations of the principal stress direction. So we have sigma 1, sigma 2, and sigma 3 shown by the different colors. And you can see that those rotate significantly. So this model was then placed under a regional state of stress. And you can see that that regional state of stress is significantly modified as a function of the geometry of the salt and its local reorientation. And so the way that we can model that is using a method called elastic dislocation modeling. It's been used in the past by King et al. 2012 to try to predict what the state of stress is in salt basins. It's based off the idea of treating the salt sediment interface itself as a triangulated dislocation in an elastic medium. And if you allow for opening and closing mode in the dislocation, that also allows the salt sediment interface to deform if that's preferable in the regional state of stress. And so we can observe what the changes are in the state of stress from the regional to the local scale. Now, it's important to understand what the state of stress is around salt for a bunch of different reasons. One of those reasons is that people drill wells near salt and need to predict the state of stress adjacent to the salt for safe drilling practices. A lot of the world's most prolific hydrocarbon basins are salt basins. Additionally, we store, in so much as the United States stores nuclear waste, we store it in salt. So understanding the state of salt and the nature of failure adjacent to it is important for that kind of application as well. So there's been a lot of studies of the state of stress around salt, and it's been observed that near, really proximal to salt walls and salt diapirs, you can have a significant elevation of the magnitude of stresses relative to regional stresses. We also can see evidence for the fact that stresses are reoriented near salt diapirs, for example. We can see evidence of that extracted from a 3D seismic reflection volume, and you can see this kind of non-patterned polygonal faulting pattern becomes oriented near the salt, which reflects that change of stress adjacent to the salt. But for these subsurface applications, there's not a lot of empirical data. You can imagine you'd only drill a couple of wells in them. And so there's a real need for analog studies of this using surface data to ensure that the methods that are used to predict things in the subsurface can be validated by surface observations. And so we're going to look at fractures. Why would you study fractures? Well, first of all, they reflect the state of stress in the basin when they formed. And so they can help us observe the stress conditions adjacent to the salt. Additionally, they are potentially conduits for fluids, as we can see here with these bleaching fluids near the horse corral in Salt Valley. And there has been multiple previous studies of fractures adjacent to these salt walls in the Paradox Basin. The regional fracture sets here are iconic. They're in every structural geology textbook because they're so spectacularly exposed. And the advantage to that is you can see a lot of them. The disadvantage is you have to manually pick a lot of them. And so one of the things that we're continue to be working on is algorithms for auto detection of these fractures from satellite data. I'm not going to talk about the details of how we're doing it too much because I don't have a lot of time and I don't know who all would be into that. But if you are into it, send me an email and I'd love to talk about it some more. And so basically what it involves is a bunch of image processing to remove the pixelation effects, and we're using sub-meter spatial resolution data, and then using a multi-scale application of a Hoff transform and then an algorithm to co-locate those to extract features along specific orientations and to detect their lengths. So just to give you an example of how it works, this is running the algorithm on a really nicely exposed pavement in the Jurassic sandstones in the Paradox Basin. And you can see that we've detected the two main fracture orientations pretty well here. And, you know, we can extract their quantitative orientations. And so we can see what fracture orientations are in the basin, and then we can use this boundary element modeling approach to try to figure out what state of stress led to their formation. And again, we're using this model. Here's just a little teeny snippet of it. This is the model I'm going to show you now, which is a little bit bigger. And then this is the whole model, which takes a really long time to run. And so we're still working through some of that. And the red dots are the well control, just to give you a sense of where we have wells that constrain the geometry of the salt and the geometry of the overlying and underlying sediments too. So I'm gonna skip right to the answer. So when you apply the modern day state of stress to the known geometry of the salt walls, you end up with a displacement of the salt sediment interface that looks like this. So I've rotated this a little bit. So this block right here, I've now rotated counterclockwise about 30 degrees. So north is now pointing this way, just so it fits on the screen a little bit better. What you can see in here in black, these are the salt welds, and what's in pink are the salt walls. And you can see that given the modern day state of stress, there are some parts of the salt that want to move a lot. Over here, this is representing propagation of the weld further towards the north. And there are some parts of the salt that don't want to move very much under the current day state of stress. Those are in blue. And if given that change in geometry of the salt, we can then predict what the state of stress is given elastic conditions of the rocks adjacent to the salt. And if they were going to form a fracture, what would that ideal orientation be? And that's what's shown here in this wild looking diagram. So what's shown here is that these would be the ideal fracture orientations predicted by the model, but thresholded on whether or not the predicted fracture would dip at greater than 60 degrees on the assumption that that's what we're able to see well with the satellite data. And so anywhere that's white, you aren't predicting high angle fractures, but anywhere that's dark, you are. Some of these fractures are joints and some of them are shear fractures, but I've plotted them all here with just their azimuth to show that in general, they will match pretty well with what we actually observe. So if we just zoom into a couple of different places, we can see that these are a pretty good match. If we look down here, this is the southern end of Spanish Valley, just south of Moab. You can see a rotation in the orientation of these regional fracture sets adjacent to the salt wall, which sits right over here. We reproduce that in this boundary element model pretty well. I should say I don't like using the word pretty well. One of the things that is part of our continuing work is establishing quantitative fitness for these and using that as a means of improving our modeling even more, which is part of the basis of collaboration that we're building with Aramco's research lab starting this summer. So if we go up here a little bit further north in the basin, this is above one of the salt welds, which is black here. And you can see that we're predicting vertical fractures above the salt weld. What we can zoom into right here is that we only predict vertical fractures above the weld. And when we look at the outcrop, we see that that is well reproduced as well, which was a surprise to me. I hadn't expected that going into it. But you can see that we're seeing, in general, pretty good prediction of the orientation, the azimuth of these fractures, but we also are predicting pretty well where we would cease to see fractures forming. And this is therefore predicting where we don't think we're above a weld anymore. Considering how sparse our data control is on where we have welds based on where we have wells, I was surprised at how well that matched, actually. This is above the weld on the northeast side of Salt Valley. And you can see that we, predict that this weld has this kind of orientation, it has a few wells in it. And so we have some control on that. And you can see that the orientation of the fractures deflects around that, and that is reproduced in that nice pavement that was shown in the Lorenz and Cooper example. And even in this location where you're rapidly changing orientation, you can see the interaction of the two joint sets coming in and interacting with each other. And so the fact that these joint sets, I already said they're joints, these fracture sets are in pretty good accordance with the modern day state of stress gives us some confidence, and more so than other states of stress you can imagine would have been possible in the past. Gives us some confidence that these are forming due to exhumation in something like the modern day stress field. And so something post-Laramide during the exhumation stage of the basin is when these fracture sets are forming, and they're joints if you go up and look at them. And these joints are really important. These are the ones that form the iconic fins that are where the Arches and Arches National Park are taking advantage of these regional joint sets. So now that we have a pretty good handle on the orientations of the modern day state of stress, we can look at faults that exist in the basin. And we can, for example, say, if you just assumed regional state of stress, you might think that they have particular likelihood to slip or likelihood to dilate and be conductive for fluids. But because the stress field is so significantly modified locally, we can see that that is really different. And we can see some parts of the basin, for example, that we predict have pretty high probability for fluid conductivity. If we go up to that part of the basin, that's this part that we looked at before here, where these fractures coming off of this basin bounding fault appear to have conducted fluids in the past. So these aren't the only set of fractures in the basin, and I would argue that there's an even more interesting one that takes advantage of the fact, again, that salt is exceptionally weak. And because we know that salt is very weak and we know its geometry in the basin here pretty well, we can take advantage of that to tackle some thorny problems that structural geologists have been arguing about for a long time. And in particular, that is the idea of what happens under low differential stress. And so this is the paper that Lauren is just about to submit. And so you'll see the figures are lovely. To take you back to your structural geology class, whether you like it or not, I'll remind you that when rocks fail, when they have a state of stress that's sufficient to exceed the strength of the rock, in compression, that failure occurs as a mode 2 shear fracture. In tension, that occurs as a joint. But in between those two, there is a curved part of the failure criteria under which it's possible that they undergo hybrid failure, which is some component of shear and opening mode fracture. And so this is typically called the Coulomb failure criteria, the linear part of the curve, and then the curved part over here in the tensile side is typically called the Griffith criteria. And so it's long been debated whether or not failure occurs under these conditions at all. Terry Engelder, who has studied fractures for decades, you can see his quote here, reference to the parabolic portion of the Coulomb-Moore envelope over the tensile portion of the normal stress axis is ill-advised for prediction of fracture propagation. So he, as recently as 1999, felt like there wasn't very good evidence for failure under those circumstances. there has been subsequent experimental investigation of this. And in particular, this is all predicated on this assumption here. So when you fail and intersect the failure criterion, the orientation of that failure is a function of the angle between the principal stresses and the tangent. And so that angle, you can see, will decrease systematically as you fail under lower and lower differential stress conditions until eventually it becomes parallel to sigma 1. And so that systematic change in orientation is part of the evidence, but that was reproduced in the laboratory by Ramsey and Chester in 2004. They did a series of these cool dog bone tests, which are capable of getting really finely resolved failure under those conditions. And you can see that there's joints, hybrid fracture, and shear fractures that form pretty systematically. So that was helpful evidence in favor. And then the person who's really taken up the cause most recently is David Farrell, who has published a series of papers, especially looking in West Texas, at how the angle that faults propagate through a multi-layer rock very systematically as a function of the strength of that rock. And he argues that these are occurring under transitional tensile conditions, and that is what's responsible for this change in orientation of the faults. And when you look at them in detail, you see that there are parts of the faults that have slicken sides on them and parts of them that show evidence for opening mode because there's euhedral crystal growth in there. And so this has been the most compelling evidence that transitional tensile deformation and failure along that parabolic part of the curve actually occurs in nature. The trouble here is that we don't know for sure what the state of stress is in this situation because it's a paleo system. We walk up to this outcrop today and we don't have anything to calibrate it against. But we can take advantage of the fact that when we're looking at salt, we know that the salt itself can't sustain any differential stress at all. So as we move further and further away from the salt sediment interface into the adjacent sediments, we know that we're monotonically increasing our differential stress spatially. So we can take advantage of that to see if there is failure along the parabolic part of the curve. So as a case study location, we chose the northernmost salt wall here, Salt Valley. We zoom into even the northernmost section of that, and we're up here, right here. Arches National Park boundary is right there, so we're just north of that. And there's this beautiful outcrop of the Curtis sandstone. There's a Jurassic sandstone that outcrops over a really large area. And we can see those big regional joint sets in here really clearly in the aerial photography. But if you zoom in closer, there is another set of fractures in there, and they are iron stained in here. They're a very distinctively different set of fractures. This is what they look like out in the field. This is kind of looking at them in their cross-section view, and you can see that they're conjugate pairs. I'll demonstrate that later. Here's our field dog, Henry. No relation to my son, Henry, but they are buds. And you can see these conjugate shear fractures in here as well. Here you can see them, again, Henry for scale. We're looking out here into the Salt Valley. This is the salt itself, and here are these conjugate fractures adjacent to the salt. And so when you're really, really close to the salt, this is what they look like. They look like they have a really narrow dihedral angle. So angle between the conjugates is really, really narrow when you're really close to the salt. So I can step through and show you what they look like. Here they are here. This is at locations A and B. You can see the angle is really narrow. As you step further away, the angle gets wider. Step wider, you step a little bit further away, now 200 to 300 meters away from the salt sediment interface. And you can see that the angle gets wider yet and wider yet. And so these sites A through G are the location of field stations where a whole bunch of these conjugate pairs were mapped. And so this is what they look like at A. This is a stereo net for those of you who haven't taken structure in a long time. Shout out to my structure class people who are here because we just talked about these. So what we're looking at are the orientations of two planes projected onto a lower hemisphere, and the poles are given over here. So you can see we have set 1 and set 2, and the average angle between the two at station A is 21 degrees. By the time we get to B, it's 31.6 degrees. At C, we are at 35 degrees. At D, we are at 37. At E, we're at 50. At F, we're at 55, and at G, we're at 56 degrees. So we can see that we're systematically increasing the angle between these two conjugates over time. So you might ask yourself, how do you know they're really conjugate shear fractures? So Lauren has collected this data. So what she went up and did was picked out the locations at specific conjugates where one cross-cut the other. And then those are all mapped in blue, and where the other one cross-cut, that is mapped in orange here. So you can see at this particular location that these are mutually cross-cutting sets. We can see that this one cross-cut this one, and vice versa for these other orientations. So that's what's shown here. But the other cool thing that we can see here, which is very tantalizing, is that the what's shown here is the orientation of that conjugate intersection as a pole to the plane, or as a line, which is a point on our lower hemisphere projection. And remember, the orientation of the intersection of two conjugates gives us the orientation of sigma 2. So the intermediate compressive stress direction. And so what we can see here is that that orientation is changing over time. So really near to the salt, less than 200 meters, the orientation of sigma 2 is nearly horizontal. And by the time we get 300 to 400 meters away, then our intermediate compressive stress direction is vertical. So we're actually rotating that systematically over time, which we think is a function of how the triaxial stress state is varying as a function of distance away from the salt. So I will really quickly mention that we did some geomechanical characterization of these exact rocks. So we took the Curtis, and this was analyzed in John Kemeny lab in geologic engineering with the help of David Streeter and George and Chad Julius. And what we can see is this is the failure criterion that was developed by doing a series of different rock geomechanical laboratory tests for these sandstones. So what you can see is that the parabolic part of the curve is actually all over in the compressive side. So it's not over here in the tensile side, like you might have guessed. It's actually over here in the compressive side. It looks like this. And if you think to like, typically, what do you think about in structural geology? You think that failure falls along a linear criteria, a Coulomb criteria in compression, and the curved part is over in the negative side, the Griffith criteria. But what we found for these rocks is that this actually all lies on the compressive side and is best fit by a Hook and Brown criteria. This is something that engineers know about because they study low differential stress failure all the time. But this is, as far as we know, the first time that this has been documented as occurring naturally with this kind of field analog. And so the cool thing about this is we've taken advantage of the fact that the salt has this very peculiar mechanical behavior, doesn't sustain shear stress, and taken advantage of that as a known boundary condition where we can increase differential stress with distance away from that salt sediment interface. And what we can observe is that when we're failing on the parabolic portion of the failure criterion, we can systematically see an increase in the angle of conjugate shear fractures. And that's in the compressive side, which is hinting to us that as structural geologists, we should care about this Hook and Brown criteria maybe a lot more than we do. What are we doing now? We have collected a really big drone-based photogrammetry outcrop. So we now have a virtual outcrop of this entire thing. If we zoom into this little cube here, you can see these big gaps. These are the weathered out joints, the big regional joints. And if you zoom in, you can see these red iron stained conjugate shear fractures. So now we can take what we know from our control stations and extrapolate that out over this huge area, because we have this fabulous, nicely georeferenced virtual outcrop. And then we can extract the same kind of data and have a lot more confidence confidence that our observations are robust and that they're spatially complete. So why should you care? Well, rock failure under low differential stress conditions occurs in a lot of applied settings. So this tells us something really fundamental about how rocks fail. It's a really unique opportunity to observe that, but it has a lot of practical applications too. For example, in mining engineering, you have low differential stress near mine walls. And so you will care how the rocks fail adjacent to walls. These are focal mechanisms observed near an underground mine, for example. So understanding the context for that is important. And additionally, failure in overpressured rock units. These are again going to be failure under low differential stress conditions. Just as an example, in overpressured shales, what's shown here is overpressure, how many wells had significant overpressure in them, and then which pressures were associated with induced seismicity. And so if we want to understand induced seismicity, we need to understand, apparently, failure under low differential stress conditions. And then near magma chambers. So we know in magma chambers, you're not going to sustain significant differential stresses. And so shear failure adjacent to magma chambers is probably going to be governed by these same kinds of fundamental rock failure, parabolic failure in the compressive side. So that's all. Salt is peculiar. It creates some unusual structures, which is a great opportunity. It forms these first order weird structures like salt walls, halokinetic sequences, cryptic shortening, transverse faults. Second order, it really reorients the stresses, which is demonstrated by the fractures, which has a lot of implications for what can be good conduits for fluid migration. But it's also a great opportunity to document some things about the fundamental nature of how rocks fail. By taking advantage of the fact that we know salt is so weak. So, and it has illuminated the idea that we need to be cognizant of this parabolic failure criteria in geologic systems. So that's all, and I'll take any questions.
All righty, thank you, Amanda. We have some time for questions. So you can either raise your hand or you can just type your question in the chat and I can relay that question over to Amanda.
I have a question. Can I just ask?
Go for it, Andy.
Yeah, so this doesn't have anything to do with Paradox Basin, but I've always been curious about these salt glaciers that you see in super dry areas. The photographs I've seen of them in Iran and the Zagros Mountains. So how do those things form? How do you actually have salt? What are the stresses that are involved in causing it to actually come and flow up out of the ground?
Yeah, that's a great idea. So or question, I don't have a slide to talk to it, but whether the salt comes out and flares up and makes a canopy, which a salt glacier would be, or whether it tapers up to narrow nothing, is a function of the sedimentation rate, or like the loading rate versus how much salt is available. So if there's a lot of salt available and you put a load on it, it kind of squeezes up and makes a salt glacier. So it's just a balance of those two forces.
Thank you.
Yeah. There's some really cool documentation of that with 3D seismic data, and the geometry of those is called halokinetic sequences. And Kate Giles and Mark Rowan have written some really cool papers about those.
Oh, okay. So, Amanda, while y'all were hiking around out there in the Salt Valley, I was wondering if you saw any correlation between fracture patterns and the occurrence of some of the mineralization, like there's little manganese oxides and then iron carbonates and so on, some of which you highlighted along the fractures. Do those follow a particular fracture orientation to your knowledge?
Well, the most noticeable one, so these big regional joint sets, for the most part, are not impacted differentially. So it looks like they kind of came along after bleaching had occurred and don't seem to have much of a preferential difference. But those conjugate shear fractures do have that iron staining. And so I don't know what the origin of that iron is, whether that's residual and it's just trapped by the loss of permeability in the shear fracture, or I'm not sure. But that's the one thing I can think of. I don't know if Lauren's on here, if she noticed anything else. It's a good question. Need to go back out.
Amanda, there's a question. Sorry, go ahead, Laura.
Oh, sorry. I was just gonna say the iron stain fractures, even looking at the shear fractures, there's generally kind of two dominating orientations. And I don't know about the mineralization specifically, but you see iron staining more commonly on the fractures that are oriented subperpendicular to the salt wall. The fractures that are oriented subparallel to the salt wall tend to have less iron staining in general.
Awesome, thank you.
So I didn't mention this, but Lauren is going to be doing an internship this summer with the Aramco Research Lab to try to do some more specific state of stress modeling. So hopefully we'll be able to contextualize all of those changes in sigma 1, 2, 3, but then also which ones are good conduits for fluids should come out of that too.
Amanda, there's a question in the chat from Steve Lingray, and the question is, how would antecedent, say, laramide fractures impact your near contemporary fracture generation?
That's a fair question. We could try to model that and see, because you would potentially reorient the state of stress near the fractures themselves too. And I haven't tried to model that. It is possible that they would cause a reorientation too, but the model already almost explodes when I try to run it. So I think I need to take a new tack on it, some different modeling tools.
Okay, if that's it, we can all give a virtual round of applause to Amanda. Thank you very much, Amanda.